Swayam Prabha. Digital India. Educated India.
We come to the last lecture of week 2. Here we will complete our discussion regarding the velocity potential equation. We will take it to its small perturbation form and then try to derive some expressions for pressure coefficient. Then we will look at hypersonic small perturbation equation and see how the perturbation equation for a supersonic flow compares with hypersonic flow. Finally, we will end with a discussion on Newtonian theory of hypersonic flow, which is based on local surface inclination. This was the last slide of our previous lecture. We recall having discussed about the velocity potential equation, reducing it from 3D to 2D form and talking about the boundary conditions which will be required to solve the equation. Now, let us try to bring in perturbations in the flow field, and we will finally impose the condition that the perturbations will actually be small, though in the beginning we start with a more general framework where the perturbations could be large as well. Now, you see that in the perturbation form, how we define the velocity components are like this, that the u component of velocity is represented by its free stream component v infinity plus a perturbation u hat, the v component by v hat. If it was a 3D form, then w would be equal to w hat, and correspondingly if you look at the problem from the velocity potential point of view, then the capital phi would be represented by v infinity x plus phi hat, this being the perturbation in the velocity potential. So, we understand that these are the perturbation velocities, and when we impose the small perturbation concept or the assumption, we may say that the u hat or the v hat, when they scale with the free stream velocity v infinity, they will be much less than 1. Now, we said earlier that the perturbations need not necessarily be very small all the time. For example, in the stagnation regions of blunt nosed bodies, the perturbations could be fairly large. You should remember this form, the form that connects the perturbation velocity components with the corresponding derivatives of the velocity potential in the perturbation sense. Now, if you substitute these relations that we have written on top into the velocity potential equation, then the velocity potential equation will now contain the derivatives written in the perturbation form. Now, the phi hat comes into all the terms here instead of the capital phi that we had earlier. Additionally, you have expressions where you have a form like v infinity plus del phi hat del x, which basically represents the u. The above equation is exact. We have made no assumptions till now about the nature of the flow equation, and therefore, it holds good for irrotational and isentropic flow. The perturbations that the equation can accommodate could be small or large, as long as they do not violate the basic assumptions of the flow, that is, they do not violate the assumption of irrotational and isentropic flow. We would like to bring in one more equation here in this context. For steady adiabatic inviscid flow, we can show that the stagnation enthalpy is conserved. the H naught is conserved. Hence, we can write for the above flow by taking 2 points, one in the free stream and another in the perturbed part of the flow, the balancing of H naught. By putting all these things together into the velocity potential equation and arranging the terms, you will be finally able to show it in a form like this, where the left hand side is nice and linear, while the right hand side still contains a lot of non-linearity. Also, the u hat and v hat could be large because we haven't imposed any constraints on them as of now, that they necessarily need to be small. Now, we are going to limit our considerations and we will say that we will just look at situations where they are very small, and for the small perturbation case, as we know that this would mean you are going to have the u hat by v infinity or v hat by v infinity much less than 1, which is applicable for slender bodies at small angle of attack. The product terms involving perturbation velocities are also considered to be small, and therefore, you would have situations like this where the products would be neglected. Further, we will consider certain ranges of free stream Mach numbers. In the subsonic range, if it is varying between 0 and 0.8, in the supersonic it is above 1.2, we can show that the magnitude of the right hand side term involving del u bar del x. So, we are basically talking about this term, which is basically the coefficient of del u bar del x, that is found to be small compared to the left hand side term 1 minus m infinity square del u bar del x, del u hat del x rather. Therefore, we can ignore the right hand side term. Now, the basis of this is that if m infinity is not very close to 1, then 1 minus m infinity square is going to be a significant term, and then only the left hand side term involving del u hat del x will be significantly larger than a term like this, and therefore, under that context we can drop it. So, we are limiting the Mach number range for which that first term on the right hand side can be dropped. So, we are now bringing in more and more constraints. For approximately m infinity less than 5 or so, we can show that the term involving del v hat del y on the right hand side is small compared with del v hat del y on the left hand side. So, we are trying to say that this term will dominate over this term, because this coefficient will be significantly small if you are operating within a Mach number range of this order. So, we have imposed one more constraint on the upper limit of m infinity, and finally, the third term on the right hand side is a small term and therefore, can be neglected irrespective of the range of the m infinity value. So, that is basically this term, which is going to be small under any circumstances, and therefore, it can be neglected. You can see for yourself, because there are products of very small terms which will make it small under any m infinity range. Put together with the comparison of the order of magnitude of similar terms on the left hand side and right hand side, the PDE reduces to a form like this, which is significantly simplified to where we started from, and you can see that small perturbation velocity potential equation is basically a linear partial differential equation. However, it is approximate because we have dropped out many terms in the process. Also, it would apply only to small perturbation flow problems. That means, we cannot apply it to thick or blunt bodies at high angles of attack, and they can be applied only in subsonic and supersonic regimes, like the way we have prescribed the m infinity, and cannot be applied for transonic or hypersonic regimes. So, the limitations of Mach number is something that you have to keep in mind, the ranges that we talked about. And from this equation, if you do a little more derivation, you can show that it will be possible to go in for very simplified expressions for pressure coefficient to begin with. So, this is basically the exact relation for pressure coefficient. From there, if you start under the small perturbation framework, you can show that it is equal to minus 2 u hat by V infinity. So, this is basically a small perturbation form of Cp. We will talk about one more form later. Once again, looking at the governing equation, the way it looks when you are talking about the subsonic compressible flow, we write it as 1 minus m infinity square times phi xx, which is basically the second derivative of phi with respect to x, and phi yy, which is nothing but this, and we have purposely not put the hats anymore, because we already understand that we are dealing with perturbations. So, we are not writing the hat over the velocity potential anymore, it is implied. And when you look at this equation for the supersonic flow regime, then we write it in a form like this, where obviously m infinity square minus 1 is greater than 1, while here 1 minus m infinity square was greater than 0, and you have a form like m infinity square minus 1 times phi xx minus phi yy equal to 0. Now, if you were to solve this equation for flow over a body or surface which introduces small perturbations, so it could be flow over a thin airfoil like a very slender diamond shaped airfoil or a flat plate, or it is a mildly wavy surface or a mild hump over a surface. We are basically talking about small compressions and small expansions produced by surface curvatures of this kind. So, imagine that the surface tips or tilts upwards and tends to compress the flow locally very weakly, because we are talking about small slopes, or the flow expands because of the dipping of the surface. Then you talk about drawing a tangent to the surface at a given point, and that basically defines your local surface inclination, the theta, so to say, and the theta over here is positive, while over here it will turn out to be a negative value, and therefore, you have a Cp expression based on the local surface inclination in terms of that theta, whether it is a positive or a negative value based on compression or expansion that it is producing based on its slope value. You will have a positive Cp or a negative Cp. And remember that the Mach number in the free stream does play a role in the Cp distribution, because it figures as a term under root m infinity square minus 1 in the denominator. So, this is how the small perturbation form of the equations are tackled in supersonic flow. Let us have a brief look at how things are done in the hypersonic regime. So, we look at hypersonic small disturbance equations, and the things look far more complicated over here. We will try to explain why it is that way. I hope you can recognize in some way that this is the continuity equation, the x momentum, the y momentum and z momentum equations, and this is the energy equation in one of its possible forms, and then here on top you have the continuity equation. Now, the hypersonic small disturbance equations are basically derived from the Euler equations by substituting the perturbation forms of the velocity components. Here we have shown it in 3D, you can do it in 2D as well, and we follow the same way essentially in defining the perturbation forms of the velocity potential equation. Only order 1 terms are retained in the final form, which basically means that the equations are approximate in nature. So, beginning from Euler equation, we try to figure out how each one of the terms in the Euler equation, the continuity, the momentum, the energy work out for a hypersonic small disturbance situation, and we find that some of the terms are very small terms, and those are the ones which are dropped, they are not retained in this form. And we will try to show in the next slide what each one of those individual terms means. The rho bar, for example, the V bar dash, the W bar dash, the U bar dash, and also X bar, Y bar, Z bar, and so on. So, let us move on to the next slide to have some more details on that. As I mentioned earlier, that the perturbation velocities are defined in the same way as we did in the velocity potential equation for supersonic flow analysis. There is only slight change in nomenclature. Earlier we had put it as U hat, here we are writing it as U dash or V dash or W dash, and then we end up defining the length scales concerned. As we do so, you find a term tau coming in some of them. So, what is tau? If we consider this to be a slender body immersed in a hypersonic flow field, and there would be a shock which will be fairly tilted closer to the body because of the higher Mach number ranges that we are talking about. This is a typical base dimension of the body. This is a typical length scale that we are concerned about. If you look at the local flow velocity vector at some point on the body in this xy plane, then you can say that V dash by V infinity plus U dash is equal to dy dx, and we can show that since U dash by V infinity is going to be very small, this is almost like saying V dash by V infinity. Again, from the geometry of the problem, dy dx is of the same order as d by L, and this is called as the slenderness ratio tau, which figures in some of these expressions. M infinity when multiplied with this tau is a very significant parameter in hypersonic flow analysis, which is called as the hypersonic similarity parameter. Remember that the x length scale is far larger than the y and z, which is evident from these equations, because if all of them are order 1 terms, that means x bar, y bar, z bar are order 1 terms, then obviously x is much larger than y and z. Similarly, the u bar dash, v bar dash, and w bar dash, when you compare, you find that in u bar dash there is a tau square, while in the v bar dash and w bar dash there are taus, which basically means that u bar dash is far weaker than v bar dash or w bar dash. Then comes the normalization of pressure by a term like gamma m infinity square, tau square, p infinity, which will produce an order 1 term. Similarly, this produces an order 1 term for density. So, this is how we tackle the normalization of the different length scales, velocities, and thermodynamic parameters. To discuss a little bit about the nature of these equations and the consequent implications, hypersonic small disturbance equations can be used in hypersonic flow over slender bodies, like we had shown in that sketch. They are limited to hypersonic flow because some of the non-dimensionalized terms are of order of magnitude unity only for high Mach numbers. So, they would be unity when m infinity is significantly large, not otherwise. Conservation equations possess an interesting property. The u bar dash term can be found only in the x momentum equation. Therefore, the hypersonic small disturbance equations concerning u bar dash is decoupled from the system. So, we will go back to that slide once again to see that only this equation incidentally has the u bar dash term, in none others does it figure. So, it is essentially saying that that equation for u bar dash is kind of decoupled from the rest. The continuity equation, yz momentum equation and energy equation are first solved for 4 unknowns, and after that the u bar dash equation can be solved, whereby you get the value of that unknown at the end of the computing process. Now, the decoupling of u bar dash from the rest of the system implies that the change in velocity in the flow direction over a hypersonic slender body is much smaller compared to the change in velocity perpendicular to the flow direction, which means that u bar dash is much smaller than v bar dash or w bar dash. The 5 conservation equations represent a compressible inviscid flow field using the Euler equations. They were applied to a hypersonic slender body flow under the assumption of small perturbations. However, the governing equations still remained non-linear. Inviscid hypersonic flow in this regard is very different from subsonic and supersonic compressible flow, because the small disturbance equations for subsonic and supersonic regimes were found to be linear, and since they are linear, they can be used to generate simple solutions for subsonic and supersonic compressible flows, especially for slender bodies at small angles of attack. Such simplifications in hypersonic flows are either not possible or very rare. The hypersonic small disturbance equations are a set of coupled nonlinear PDEs for which we obviously do not have a general analytical solution. So, we are getting the feel that hypersonic equations are nonlinear in nature and they have some inherent differences with respect to the flow equations for subsonic and supersonic regimes. We will begin discussion about the Newtonian flow, which is the last thing we will discuss in this week. We have seen the surface inclination based results for supersonic flow, where the theta parameter has an influence on the Cp, theta being the angle of compression or expansion due to the local slope of the surface, and it has a dependence on m infinity. Newtonian theory is also a surface inclination based technique. It is applicable for hypersonic flow, and it was first proposed by Newton several centuries back, where he argued that when we immerse a surface into a flow field, basically the fluid elements come and meet the surface by following rectilinear paths, and then when they meet the surface they just turn in such a manner that further onward they just follow the surface profile and move tangentially to it, which would basically mean that they lose all their normal component of momentum on meeting the surface. Behind the surface not much happens, because basically due to the rectilinear propagation of the fluid elements there is no flow turning which can happen, and based on this theory, when low speed flows were tackled there were severe anomalies. However, in this era where hypersonic flows are increasingly studied, it was found surprisingly that Newtonian flow model fits in so well into this framework. So, moving on with this discussion, we say that the change in normal velocity component of the flow when it meets the surface is v infinity sin theta, that is the change in velocity delta v in the normal direction. The mass flux incident on the surface is basically rho infinity v infinity into the projected area, like the way it is shown here, where A is basically the length of that plate, and let us call that as m dot, and time rate of change of momentum of the mass flux striking the flat plate would be m dot into delta v, which is again according to Newton's second law the force acting on the plate, and given by the expression rho infinity v infinity square A sin square theta. Force per unit area would give us the pressure. However, this pressure is purely due to directional motion of the fluid particles. because Newton did not talk about the random motion of the particles which would lead to static pressure, and therefore, essentially he talked about P minus P infinity, giving rise to the rho infinity V infinity square sin square theta expression. Plugging it into the Cp expression that we know of, P minus P infinity by half rho infinity V infinity square, we come out with an expression 2 sin square theta. Surprisingly, this result has no Mach number dependence. That means it is basically a Mach number independent result, unlike what we saw in the supersonic regime. Now, we find that in hypersonic flows, in reality, when the flow meets the surface, the shocks which are formed on the surface lie very close to the surface, and therefore, when the flow moves past the surface, it turns practically tangential to the surface, and that seems to match fairly well with the model that Newton had prescribed for the flow many centuries back, though probably he did not think about the issues that we are talking about over here, but there is significant similarity between the two kinds of flows, and therefore, the result gives us fairly good estimates of pressure on slender surfaces immersed in a hypersonic flow field. We conclude this lecture by saying that small perturbation velocity potential equation was discussed in this lecture. Subsequently, pressure coefficient equation for supersonic small perturbation flow was discussed. Hypersonic small perturbation equations were discussed without any detailed derivation. Also, we talked about the nonlinear nature of such equations compared with the linear nature of small perturbation equations in the supersonic regime. Newtonian theory of hypersonic flow was discussed, and the pressure coefficient based on local surface inclination was derived. It was found to be Mach number independent, while the corresponding surface inclination result for supersonic flow was found to have a dependence on both surface inclination and the free stream Mach number. Thank you.